Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to YouTube channel Chandan Physics. In this video, we are going to discuss Lorentz gauge. Let's begin. We have already known that the two coupled Maxwell's equations in terms of electromagnetic vector and scalar potentials. Two equations, one in terms of scalar potential, another in terms of vector potentials, that is grad square A minus mu epsilon del square A divided by del T square minus grad dot A plus mu epsilon del phi by del T is equal to minus mu J, and another one grad square phi minus mu epsilon grad square phi divided by del T square minus grad dot A plus mu epsilon del phi by del T is equal to minus rho by epsilon. These two equations are already derived in the chapter named as scalar and vector potentials, means Maxwell's equations in terms of scalar and vector potentials. Here that equation 1 purely in terms of vector potential when that bracket term will be 0, and again in equation number 2 it will be purely on that of scalar potential when that bracket term will be 0. To create that bracket term is equal to 0 is that condition which is called Lorentz condition. Using Lorentz condition, grad dot A plus mu epsilon del phi by del T is equal to 0. Then equation number 1 and 2 becomes, then equation 1 under 2 becomes grad square A minus mu epsilon del square A del T square is equal to minus mu J. And equation number 3 and equation number 2 changes to grad square phi minus mu epsilon grad square phi del square phi del T square is equal to minus rho by epsilon. That is equation number 4. By using that Lorentz condition, equation 1 and equation 2 reduced to that of equation number 3 and equation number 4. If that scalar potential and vector potentials satisfy that Lorentz condition, then that type of gauge is known as Lorentz gauge. If the scalar and vector potential satisfy Lorentz condition, Lorentz condition, that quantity is equal to 0, then that type of gauge is known as Lorentz gauge. The gauge is known as Lorentz gauge. Again, these two equations can be reduced but V square is equal to 1 divided by mu epsilon, where V is the phase velocity of the wave. That is why mu E is equal to 1 divided by V square. Therefore, equation 3 and 4 changed to equation 3, the grad square A vector minus 1 by V square del square A del T square is equal to minus mu J vector. From this, we write grad square minus 1 by V square del T square of A vector is equal to minus mu J vector. That term is denoted to an operator, and that operator is called D'Alembert operator, and it is written as a square box. Square box represent 4 coordinates, 3 position coordinates and another one time coordinates. Basically, that type of operator is used in that of space time relative phenomena. So, grad square box square A vector is equal to minus mu J, where grad square is equal to square box square is equal to grad square minus 1 by V square del square by del T square, which is called D'Alembert operator. In some books, it is written as only box, no confused, as that the box square is nearly equal to that box. These two are invariant. Therefore, that operator either written as square or only in box. That is equation number 5th. Again, equation number 4 change to, and grad square phi minus 1 by V square del square phi by del T square is equal to minus rho by epsilon, or grad square minus 1 by v square del t square of phi is equal to minus rho by epsilon. That is an operator, D'Alembert operator. 4 sides represent 4 coordinates, 3 position coordinate, 1 time coordinate. Basically that type of operator is used for space time phenomenon indicating way. Minus rho by epsilon. Equation number 6. Equation number 5 and equation number 6 are similar to that of Poisson's equations. Equation 5 and 6 are similar to that of Poisson's equations. And they can be solved by similar method to solve that Poisson's equations. Okay. From Maxwell's equations in terms of vector and scalar potential, using that Lorentz condition, we reduced these two equations, and that equation if satisfy the scalar and vector potential, then that type of gauge is called Lorentz gauge. And a modification to equation number 3 and 4, and these two are in the form of Poisson's equations. Now we can show under that of gauge transformation, either that Lorentz condition is invariant or not. To showing this, using gauge transformation, vector potential since A dash as A plus gradient of some scalar function psi, and that scalar potential change to this phi minus del psi by del t. These two are the condition of gauge transformation. Now these two conditions are used for Lorentz condition. In Lorentz condition, grad dot A plus epsilon mu del phi by del t is equal to 0, or grad dot A in place of mu e 1 by v square del phi by del t is equal to 0. Now under that of gauge transformation, the Lorentz condition changes to, under gauge transformation, the Lorentz condition will be under Gauss transformation, the Lorentz condition will be, here in place of A we substitute, that is A dash minus grad psi. In place of phi we substitute phi dash plus del psi by del t. This grad dot, in place of a vector, that is A dash minus grad psi plus 1 by v square del by del t. In place of phi, that is phi dash plus del psi by del t is equal to 0. Grad dot A dash minus grad square psi plus 1 by v square del phi dash del t plus 1 by v square del square psi by del t square is equal to 0, or grad dot A dash plus 1 by v square del phi dash del t is equal to grad square psi minus 1 by v square del square psi del t square. Look here, if we say that one is the Lorentz condition at gauge transformation, it will be invariant when that term will be 0. Let we take it as equation number 7. The Lorentz Gauge condition is said to be invariant under gauge transformation when in equation number 7 grad square psi 1 by v square del square psi del t square is equal to 0, means grad square 1 by v square del square del t square over that of psi is equal to 0, which one is D'Alembert's operator psi is equal to 0. When that D'Alembert's operator is equal to 0, then that entire term will be 0. Therefore, we can say that the Lorentz condition is invariant under that of Gauss transformation. Okay. So, here with the help of this video lecture we understand the concept of Lorentz Gauge. This is the Lorentz Gauge condition. By using that Lorentz condition, by using Lorentz condition, that equations reduced. Next, we show under Gauge transformation that Lorentz condition is invariant. Using Gauge transformations, and we show that Lorentz condition is invariant under that of Gauge transformation when that term will be 0. So, it is useful. and informative notes, let me wind up the session. Thank you.